Section: Introduction. In this section, we discuss how in recent times, general-purpose generative models, particularly large language models, LLMs, trained on vast amounts of unlabeled data, have seen significant success. We recognize that training these models to exhibit desired behaviors can enhance their utility. However, controlling these behaviors when the model is actually being used, known as inference time, remains a challenge. Despite their advancements, these models often struggle with tasks that involve following instructions, reasoning, or handling complex and unconventional instructions, including logical operations like negation. A specific challenge we highlight is teaching a model to avoid discussing a certain topic when asked to do so. Interestingly, when we mention the topic in the model's prompt as something to avoid, it paradoxically becomes more likely to talk about it, a phenomenon similar to the pink elephant effect in psychology. In our paper, we explore the issue of controllable generation through what we call the pink elephant problem. This involves instructing a model not to talk about an undesired topic, the pink elephant, and instead focus on a desired alternative, the gray elephant, as illustrated in our example dialogue. To tackle this, we introduce a new approach using reinforcement learning from AI feedback, RLAIF, which we name direct principal feedback, DPF. Previous studies have shown that RLAIF can enhance a model's ability to stay on topic, reason effectively, and reduce the chances of making things up. However, it has been difficult to teach a model to consistently avoid a specific topic, even with fine-tuning and careful prompting. Our main contributions include presenting the pink elephant problem as a new challenge for language models, introducing direct principal feedback as an innovative RLAIF approach that uses critiques and revisions in natural language as AI feedback, and demonstrating how models can be trained to follow new behavioral rules dynamically at inference time. This involves training our models to avoid any pink elephant topic specified during use. We also share our methods for creating synthetic preference data, along with our models and codebase, hoping they will be useful to the community. Furthermore, we discuss how traditional methods for preference learning and fine-tuning involve pre-selecting behaviors or rules, which limits the ability of models to adapt to new or unique requirements from different users or deployment scenarios. Our approach with DPF allows for more flexibility, enabling models to be fine-tuned to follow preferences that can be specified dynamically, based on the context in which they are deployed. This not only makes it possible to address the pink elephant problem by avoiding specific topics as needed, but also improves the model's utility across a wide range of tasks and deployment scenarios. Lastly, we simplify the RLAIF process with our direct principal feedback approach. Traditionally, RLAIF involves a multi-step process that includes fine-tuning a model on helpful examples, critiquing and revising these outputs, and then using these revised outputs for further fine-tuning. Previous attempts to streamline this process have omitted the critique and revision step, focusing instead on directly ranking model outputs. While this simplification has its benefits, it falls short of teaching more complex behaviors. Our DPF method, by contrast, leverages the natural pairing of responses before and after revision to fine-tune models in a way that instills complex behaviors more effectively, offering greater control over the learning process. This approach not only differentiates our work from others but also opens up new possibilities for controlling model behavior in nuanced and sophisticated ways. Section Summary. In this section, we introduce the pink elephant problem, where language models struggle to avoid discussing specific topics when instructed. We propose a novel approach called direct principal feedback, DPF, to enhance controllability in models by training them to dynamically adhere to new behavioral constraints at inference time. By simplifying reinforcement learning from AI feedback, RLAIF, with DPF, we enable models to be controlled without hard coding values, allowing for more tailored preferences and easier deployment in various scenarios. Section: Applying DPF to the pink elephant problem. In this section, we discuss how we applied the dialogue preference filtering, DPF, method to tackle the pink elephant problem. Given the challenge of creating high-quality pairwise preferences for this problem, we found it more effective to use revisions to produce a dataset that exhibits the behaviors we're aiming for. The pink elephant problem, which involves nuanced differences between dialogues about pink elephants and those about the desired gray elephants, is better suited for DPF rather than a ranking-based approach. This is because a ranking-based method would struggle to accurately capture the subtle distinctions we're interested in. To create our dataset, we gathered 162,000 multi-turn conversations that revolve around the pink elephant problem, covering 29 varied fields such as sports, health, business, and politics. The process of assembling this dataset required about 2,000 hours of computing time on A100 GPUs, with an additional 20,000 to 30,000 hours spent on prototyping. The first step in our dataset creation was to generate a wide array of topics for our chatbot to discuss, aiming for a high level of diversity. This approach aligns with our belief, shared by others in the field, that diversity is crucial for generating high-quality synthetic data. We used GPT-4 to come up with 200 potential topics typically found in daily conversations. After generating this list, we manually sifted through it to ensure the topics were relevant for everyday discussions and suitable for a chatbot's use in real-world applications. We removed topics that didn't meet these criteria, such as the legal system of extraterrestrial life. The refined list includes a broad spectrum of subjects, from travel and careers to sports, health, festivals, and religions. Next, we focused on creating approximately 2,500 pink elephant pairs, PEPs. These pairs were crafted using GPT-4, with the aim of producing similar yet distinctly different pairs. For instance, we wanted dialogues about a gray elephant to naturally progress towards mentioning a pink elephant. To achieve this, we prompted GPT-4 to generate 100 pairs of topics and their top alternatives or competitors. We then manually reviewed these pairs to ensure they met our criteria for pink elephants, confirming that they were indeed alternatives with identifiable differences. Examples include the pair Nike, Adidas, for the sports topic, and Taj Mahal, Ellora Caves, for tourist destinations in India. A selection of these pairs is available in our PEP table. For the bulk of our dataset generation, we employed stable Beluga 2 to 70B with a best-of-n strategy, setting n to 2 and ranking the outputs based on generation perplexity. Generating unwanted behavior was another crucial step. This involved creating dialogues where the chatbot mentions a pink elephant despite instructions to the contrary. To ensure a diverse range of conversations that could naturally lead to mentioning a pink elephant, we first generated 50 attributes that could bridge the gap between contrasting PEP pairs. Using these attributes, we aim to produce examples of dialogues that represent failures of the pink elephant problem. We noticed that adding a planning step before generating dialogues resulted in more natural and high-quality conversations. To further improve the quality of our dialogues, we introduced a dialogue planning step. Here, we first asked our model to generate a plan for a conversation that would shift from discussing a gray elephant to a pink elephant. Following this plan, we prompted stable Beluga 2 to 70B to create a dialogue based on the plan and the PEP. Although we discarded the plan afterward, this intermediate step significantly enhanced the dialogue's naturalness and the likelihood of ending with a mention of the pink elephant. This planning step is a novel approach not typically seen in other data generation methods for reinforcement learning in artificial intelligence foundations, RLAIF. We've included examples of the prompts used, along with sample dialogues and plans, in our dialogue planning table. Section Summary. In this section, we applied dataset pairwise filtering, DPF, to address the pink elephant problem by curating a dataset of 162K multi-turn conversations across various domains. We generated diverse pink elephant pairs, PEPs, using GPT-4, ensuring they were contrasting yet related, and introduced a dialogue planning step to improve the quality and naturalness of the resulting dialogues, ultimately leading to successful mentions of the pink elephant as intended. This innovative approach of incorporating dialogue planning and data generation significantly enhanced the fluency and relevance of the conversations, setting it apart from traditional methods in reinforcement learning from human feedback, RLAIF, data generation. Section: Revised behavior generation. In this section, we discuss how we create examples of good behavior, specifically focusing on instances where our chatbot successfully avoids mentioning the pink elephant. To achieve this, we first identify negative examples where the chatbot incorrectly brings up the pink elephant. We then use a model named Stable Beluga 2-70B to critique these responses and suggest revisions that steer the conversation towards the gray elephant instead, ensuring the pink elephant is not mentioned. Interestingly, we discovered that including the initial plan in the revision process didn't help remove mentions of the pink elephant. So, we decided to exclude the plan during the critique and revision stages. This approach gave us pairs of data points, one with the chatbot's original, undesired behavior and another with the revised, desired behavior. Next, we cleaned the data by cutting off dialogues at the first mention of the pink elephant by the chatbot. We further refined the data by removing dialogues that didn't meet certain criteria, such as those where the pink elephant was mentioned too early or not at all in the desired parts of the conversation. To filter these dialogues effectively, we used techniques like Levenshtein distance, Hamming distance, and cosine similarity, with the help of Distill-Burt embeddings for efficiency. We set a cosine similarity threshold of 0.8 to balance data quality with the quantity of examples retained. The dataset was then divided into training, validation, and test sets in a 96% to 2%-2% ratio, ensuring no overlap of data points across these subsets. For our experiments, we focused on using a technique called DPF with our dataset to train models to avoid mentioning the pink elephant. Since our dataset includes examples where the chatbot needs to navigate away from the topic of the pink elephant, it wasn't suitable for direct behavior cloning. Instead, we opted for DPO fine-tuning without an additional SFT step, starting with models that had already been trained with SFT. We chose the Open Hermes 7B and 13B models for their strong base and compatibility with our dataset. Our training utilized B-Float 16 precision, a global batch size of 64, and the RMS prop optimizer, aiming to maintain baseline performance while enhancing the model's ability to avoid the pink elephant topic. We decided on a relatively large beta value of 0.5 for DPO and conducted our training over 3 epochs, though we ultimately used only 1 epoch for our final models. We compared our fine-tuning method against several baselines, including the base Open Hermes models and others prompted to avoid the pink elephant, like Llama 2 Chat and GPT-4. Our attempts to compare with models trained using ILQL were unsuccessful due to convergence issues, leading us to focus on DPO. For quantitative evaluation, we used GPT-4 along with human annotations to assess whether the model mentions the pink elephant. We set up a specific prompt format for GPT-4 to evaluate responses in a test set designed to elicit mentions of the pink elephant. Our evaluation showed a consistent base rate of pink elephant mentions across models, indicating that DPF does not negatively affect performance in scenarios without explicit instructions to avoid the topic. The difference in mention rates before and after applying DPF highlighted the effectiveness of our approach, with our models significantly outperforming the baselines in avoiding the pink elephant when instructed to do so. To ensure the reliability of GPT-4 as our evaluator, 2 authors independently reviewed a subset of the generated examples, finding high agreement rates with GPT-4's assessments. This confirmed GPT-4's effectiveness in this evaluation setup. Lastly, we also tested our model on several Open LLM leaderboard tasks to verify that it retained its performance after being fine-tuned on the pink elephant's dataset. Section Summary. In this section, we generate examples of desired behavior for our chatbot by applying critiques and revisions to amend negative instances, such as avoiding discussing the pink elephant. We then clean the data by filtering out dialogues that do not meet specific criteria, using measures like Levenshtein distance and cosine similarity. Finally, we train our models using DPO fine-tuning without an extra SFT step, comparing our method to various baselines and evaluating the model's performance in avoiding mentions of the pink elephant in generated responses. Section: Qualitative Evaluation. In this section, we delved into evaluating the quality of the model's outputs by closely examining them. We discovered that the conversations generated remained coherent and flowed smoothly. The models were adept at redirecting conversations in a seamless manner. For instance, if the model was not knowledgeable about photography, it might respond with, "I am sorry, but I am not an expert in photography. However, I can recommend some composition techniques for still life painting." This shows the model's ability to offer relevant alternatives when the original topic is outside its expertise. When the conversation did not directly mention the pink elephant, the models were capable of providing reasonable alternatives. However, the situation changed when the conversation explicitly involved the pink elephant. In such cases, the baseline Open Hermes models, prior to the implementation of DPO, direct prompt obfuscation, exhibited two main types of failure. Firstly, they might answer the question as if ignoring the instruction not to discuss the pink elephant. Secondly, they could become confused, initially responding to the question and then retracting by apologizing and stating they were not permitted to talk about the pink elephant. Both scenarios highlighted significant shortcomings in the model's performance. Moreover, we observed that when we specifically instructed the baseline Open Hermes models to avoid mentioning the pink elephant, they paradoxically mentioned it slightly more often, or at the very least, not any less frequently. This observation reinforced our conviction that the pink elephant issue represents a critical flaw in the model's design and functionality.